Welcome, everybody, wherever you are. Good afternoon, good evening, good morning, good time zone, whatever time zone you're in. And yes, I'm Dylan Beattie. I am here today to talk to you about there is no such thing as plain text. I just need to focus a window. There we go. That's nice. Now, this is me. I run a company I run a company on planet Earth, which is really all anyone does at the moment because everything's remote and we are all international all the time. I run a company called ASCII. I do software training, I do public speaking training and .NET systems architecture. And as of this year, it is completely online, like a lot of things. So check out what I do at ursatal.com. I'm a Microsoft MVP. Thank you, Microsoft. I run a .NET user group here in London, where I'm broadcasting from today. And I also, as Dan mentioned in the intro there, there's this phrase rockstar developer that kept coming up in job adverts and everything. And I thought, this is really bad. Like, this is a stupid expression. What if we just made it so that everyone could be a rockstar developer? So I invented a programming language called Rockstar that you can check out at codewithrockstar.com. And the good news is you type in a line of code, you press the button, and if it runs, you're a rockstar programmer. Well done. You can go and apply for all those amazing jobs on LinkedIn. And today, I'm not going to talk to you about Rockstar. I'm going to talk to you about plain text. Really, yeah, I'm going to do a full talk about plain text because it turns out there's no such thing as plain text. When we talk about plain text, like if I say to you, hey, send me a plain text file, what I mean is I don't want to do a lot of tedious configuration. Send me something I can open. Send me a file that I can just open it up and see what it says. And that carries a lot of assumptions. You know, for you to send me a file that I can open and read, you need to know what kind of computer I'm on. You need to know what languages can I read? What alphabets can I read? What kind of display am I using? Is this coming out on a screen or on a phone or on a Kindle? There are all these different complexities around plain text, because plain text is just another example of a pattern that we see everywhere that technology is used to communicate between humans. Somebody has something, I have an idea, a concept, a piece of artwork, some code, and they need to turn that into a digital form that the technology can manipulate. And then we are going to send it somewhere else. We're going to get it back out at the other end. And if it worked, the person on the other end will understand what it was that we were trying to communicate there. This happens, email, music, even this, the Teams call we're using today. I got ideas in my head. I'm sending them down through that webcam lens over there, over hundreds of thousands of miles of undersea cable. And if it works at the end of it, you're going to have some of the same ideas that I've got, and it'll be successful. So let's rewind. We're getting ahead of ourselves a little bit. We're going to start at the beginning. Now, human beings, we invented writing about 5,000 years ago, but it kind of didn't get interesting until about 150 years ago when we decided to combine writing with this fancy new thing we had called electricity. And just like I said, any information processing system, 3 steps to it. Encoding, how do we get it into the system? Processing, what do we do with it? Decoding, how do we get it back out at the other end? How do we turn text into electricity? What do we do with the electricity, and how do we turn it back into text at the other end? Now, the earliest text encoding system I could find, I think probably the earliest one there is, was used by this thing. This is a Cook and Wheatstone telegraph system. It was used here in England in the 1830s. And it was used to send signals along 5 electrical wires that they ran along the railway lines. So they could send a message saying, hey, the train is coming, or the train is late, all this kind of thing. Now, the thing about this, there are actually 2 really interesting precursors. It's 1830. And there were 2 arguments which will be familiar to anybody who works on software products. One, the engineer who built it wanted to give it away for free. The business person who was his partner wanted to sell it for lots of money. And that sounds familiar to anyone? Well done, it hasn't changed. And the other big argument they had is that they could have made it very, very cheap by requiring experts to use it. If you had trained operators at both ends of the telegraph system, they could have probably done it with just 1 or 2 wires. But they argued they would sell more units if it was easy to use. Ease of use was a consideration. And so they used these 5 wires. And the way that you read a signal off the Cook and Wheatstone system, each wire could be positive or negative. So we had a 5-symbol trinary encoding system. It's 120 years before ASCII. And what those positive and negative wires would do, you'd connect two of them together in a certain combination, and two of these needles would move. And when they moved, you'd look on that dial and you'd see where they intersected, and you'd read that letter off. That was the letter D, and then you'd transmit the next one and the next one. And so this was the first text encoding, electrical text encoding system ever used. And like I said, it was a 5-symbol trinary system. 5 symbols could be plus, positive, negative, or neutral, 0. So if you think, ASCII versus encoding versus Unicode is complicated, we started with 5 trinary bits, 5 trits. So things improved very quickly from there. Now, the Cook and Wheatstone system had a problem. These 5 wires were about 20 miles long, and first one wire burned out, so they worked out how to run signals over 4 wires, and then the 4th wire burned out, so they tried to work it out over 3. And meanwhile, on the other side of the Atlantic, a guy called Samuel Morse was working on a 1-wire telegraph system. It could just send a signal or no signal, and you could control how long the signal lasted for. And that is what gave us this Morse code. Now, actually, it's funny, the Morse code that everybody recognizes today was not the one Samuel Morse invented. Morse came up with kind of the prototype, and then a guy called Friedrich Gerke, who's a German engineer, he came up with the standardized system. And in 1865, they had a technology conference in Paris, and they decided that this was international Morse code, and it spread everywhere because this was the wave of expansion of telegraph systems. And so suddenly there was this technology and there was a protocol that was used on it. Now, if you've ever worked in tech and you've shipped software to users, you'll know when no one's using your system, you can change anything you like, right? Hey, move that window, move that button, get rid of that feature. Once you have users, changing things becomes expensive. And when your Morse code protocol is used by every telegraph system in the world, you are not changing it, ever. Morse code is still used today. Morse code itself was the dominant communications protocol for electronic communication for nearly 100 years, 1865 to 1965. And what eventually toppled it and meant people were prepared to invest in a new system was computers. Early computers. Morse code didn't work well with computers. It was inefficient. It was a time-based code. It was very difficult to store on punch cards and magnetic tape. And so in the 1960s, the American Standards Association, which would become the ASA, became ANSI, and ANSI published ASCII, the American Standard Code for Information Interchange. And we still use ASCII today, But have you ever stopped to think about what an ASCII file really is? Because there's 2 things you got to bear in mind. One, ASCII was designed to work with these things, mechanical teleprinters. And second, it was designed to be stored on cardboard punch cards. And, it's decades since anybody has used a punch card or a teletype machine, but ASCII was so successful that we are now stuck with those decisions, probably forever. Nothing is ever going to be successful that doesn't respect the conventions of ASCII that were developed for punch cards and typewriters. Let's have a look at the ASCII block. Now, we start at the beginning. ASCII is a 7-bit protocol, so it gives us 127 characters. And this first block here, 0 through 31, these were all control codes for those early teleprinters. They would move print heads around and they would ring bells and do all kinds of stuff. Now, there's an interesting legacy. Most of us ignore this today. We don't use the bottom 32, or we think we don't use the bottom 32 characters of ASCII. But there were shortcut keys in the 1960s. If you wanted a control code 1, you pressed Control A, start of heading. If you wanted to type start of text, you pressed Control B. If you wanted end of text, terminate, stop what you're doing, shortcut Control C. Does that sound familiar to anybody? Then we have Control D, Control E, end of transmission inquiry, Control 7 or Control G, which is ASCII code 7. If you go into a Windows terminal, you type echo space, press Control G, press enter, it'll go bing, because we use the same control code to ring a bell, which now is a WAV file that we used to in the 1960s. And then we've got this whole complicated block of things like line feeds and vertical tabs and carriage returns and all that kind of stuff. Now, like I said, you got to remember, these were designed to run on mechanical teleprinters. You would print a line of text, and then you would return the carriage to the start of the line, and then you would feed the paper to the next line, carriage return line feed. And if you wanted to do something like, you could print a line of text, you could carriage return, and you could print the second line again, and it would overprint it, and you'd get this kind of pseudo bold effect. Now, for historical reasons, Unix systems and Linux systems use \n as a command line, and Windows uses /r/n. This is because Linux and modern day Mac OS as well, they evolved from Unix, and Unix evolved from a system called Multics. And Multics was the first operating system ever that supported device drivers. So you could put an abstraction layer between the instructions in your text file and what the teleprinter actually did. So they used that to put in this rule that says, look, if someone puts in a new line, give them a carriage return as well. Start the new line at the end. Whereas Windows 10 is based on Windows 7, which is based on Windows, what do we have? XP, and XP came out of NT, and NT came out in 95, and MS-DOS all the way back to CP/M, and CP/M was designed to work on mini computer terminals, which did not have device drivers because that would have made them too expensive. And so here, 50 years later, Windows and Linux and Mac OS cannot agree on how you end a line of text because of reasons going back to Multics in the 1960s had device drivers and mini computer terminals didn't. Of course, .NET developers, we don't worry about that. We just do environment.newline. And in theory, that'll just adapt to whatever you're running on. Although if you're doing Advent to code and you right-click your input file, you do save as, that's a Unix text file that's on their website there. And unless you open it and save it in Visual Studio, splitting it on new lines isn't going to work because it's full of, it's going to look for carriage returns that aren't there. Let's look at the next chunk of ASCII. Now, there's some neat ideas here. These are the punctuation marks. Now, they had to make some compromises to fit ASCII into 127 characters. Like they decided just one hyphen. That could be minus sign, that could be hyphen, that could be all the typesetters characters like a N dash and an M dash. They figured we could just use one little horizontal stripe for all of those. We'll talk in a second about why that might have been a bad idea. When we get to ASCII 48, this is numbers. And there's a little bit of clever stuff here. To turn an ASCII character into its numeric representation and back again, all you do is look at the lowest 4 bits. And that was fast. You know, even the computers of the 1960s could flip from ASCII digits to ASCII numbers to digits and back again very, very quickly in both directions. Really, really neat, elegant optimization. We look at the alphanumeric block. You ever wonder why ASCII capital A is 65, but lowercase a is 97? Reason is there is 1 bit of difference between them. So if you want to do a case-insensitive comparison on an ASCII text file, you just ignore the 6th bit. And that gives you lowercase a, uppercase a become the same thing. And finally, right at the end of the block, ASCII 127 is del. It's the delete control code. The reason why ASCII 127 is delete is that in binary, it looks like this. And if you print that onto a punch card, it punches out all the holes in the strip and it erases, deletes del, the information that was there before. So that's why ASCII 127 is hanging around there. So the American Standards Association, they publish this and they go, hey, 127 characters is all you'll ever need. And the rest of the world goes, what? We can't work 127. We can't work with this. None of our letters are in here. Now, for me, I grew up in Zimbabwe, where I spoke English and we used dollars and cents. So I didn't kind of realize ASCII was a problem until I moved to the UK when I was 10 years old. And I went looking for this. And I couldn't find it. I couldn't find pound sterling because the Americans didn't include it when they made ASCII. And people all over the world were having a similar kind of process of like, I need this letter or this glyph or this character in my alphabet that's not in ASCII. And they look at ASCII and they go, hey, well, we got 0 through 127, but what about this other half? If we're using 8 bits for our characters, is anyone using this bit? And of course, ASCII wasn't using it. And so lots of people all simultaneously went, I know, we'll use the top half for our own alphabet or our own language or our own set of graphics drawing characters. And they all did it at the same time, and none of them really talked to each other. And we ended up with a big old mess. And then we came along and went, right, how do we fix the mess? I know, let's take every single one of these systems and we'll call them code pages. So that's, if you ever come across a code page, that's what a code page is. A code page is a set of rules for deciding what the second half of the 8-bit character block means right here, right now on this document on this computer. This is one of the most famous code pages of all. You've probably seen this one. This is a code page that shipped with the IBM PC. I think it's 432. And they used the upper half to draw all these cool box drawing characters so you could make little ASCII hut diagrams and play computer games with mazes. They also decided they were going to reuse the first set of 32 characters. Now, if you've ever seen an IBM PC crash really hard, you'll get these little smiley faces showing up on your blue and pink CGA monitor. That's why. It's because the bottom set, the computer has crashed so hard it's spitting out nonsense codes in the 0 to 31 control code block, and the terminal is going, oh yeah, smiley faces, playing cards, all these kinds of things. Now, there's a lot of these code pages. This is the screenshot of a chunk on Wikipedia. Microsoft had their set of code pages. There's one for MS-DOS, there's another one for Windows. Apple had one, Linux had one, IBM had one, all these different incompatible conventions about what the second half of the ASCII character block means. And this was a bit of a problem, until in the days of code pages, if you wanted to mix Russian and Hebrew inside one document, you couldn't. Impossible. There's no way of doing it. You want to send someone an email who's on a different system, maybe they'll be able to read it if you're both speaking kind of American English or some approximation. But by the end of the 1980s, whole thing is a screaming mess of incompatible formats, and we could not rely on ASCII and code pages, and we were starting to connect together computers. The internet was a thing, email was a thing. People needed a way of talking to each other, and that's where the Unicode consortium comes along. Unicode, Unified Coding System. Now, the mission statement of the Unicode consortium is lovely. It's simple, and it just says, to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Easy, huh? So let's break that down. A single consistent way, no code pages, no stateful encodings. You got to be able to look at any series of bits and know what does it mean, what language is that sequence of bits in, what character does it represent. All human languages, that's not just the modern ones, that's things like hieroglyphics, ancient Sumerian. There's people doing research on archaeology and ancient text. We want them to be able to use Unicode to document and share their research as well. All computers and devices. Well, the way to do that is you build a standard that works really well. You make it free, you take off any licensing restrictions, and you make it easy to implement so that it creates a pit of success for handset, computer operating system, device vendors. All these kind of people are like, yeah, we should just support Unicode because that's the easiest thing for us to do. Take a look at these two bits of text. Now, Unicode said they want a single consistent way of representing every single letter and symbol that's ever been used. Are these the same? Look at them for a second. They're not. They look the same. They are not the same. The first part here is Russian. This is хорошо, means good in Russian. The bottom one, same set of three shapes, but that's the middle of the English word exoplanet. So we have a H and an X, we have an O, we have a P or an R. It's the same shape. It means a different sound with a different meaning because it's in a different context pertaining to a different alphabet. So these are different letters. What about if we have these two? So this is the Russian word for tiger and the English word for tiger are pronounced kind of the same, tiger, tiger. So we got this T at the beginning, same shape, same sound, same letter. I don't know. Unicode decided no. Unicode decided that the T that belongs to the Russian alphabet, even though it's the same shape and the same sound, Cyrillic alphabet, I mean, the T that belongs to the Cyrillic alphabet, same shape, same sound, is not the same letter as the T that belongs to the English, the Latin alphabet. And it gets more interesting. Here is the word, I'm going to attempt to pronounce this. I think this is hårføner. It's a Norwegian word, and it means a hairdryer. Now, I'm British. I grew up speaking and reading British English. You know, good afternoon, this is the BBC. London is the capital of Great Britain. And so when I'm traveling, I look at words like this, and my brain just kind of edits out the bits that I don't understand. And it goes, well, that's an A and an O. I don't know what the things mean. I take them out, and I say hårføner. And everyone rolls around laughing because that is not how you pronounce the Norwegian word for hairdresser. Now, for a hairdryer. Now, when it's just me not being able to get a hairdryer, no big deal. But this kind of stuff can have consequences. Look at a typical sentence here. Introduce you to some people here. This is François Baudet, who's a French archaeologist, and this is the rock band Motley Crue. And one day, François the archaeologist went to the Motley Crue concert. Now, this sentence is written in English. This is a perfectly valid, correctly spelled English sentence, but it has these characters in it which are not part of the English alphabet. We have a C here with a cedilla, and we have an A and an E mashed together like that. We got an O with an umlaut and a U with an umlaut. Now, you might think, hey, you know, no big deal, but this can actually cause problems for some people. Let me introduce you to another friend of mine. This is Magnus Mårtensson. No, this is not Magnus Mårtensson. This is Magnus Mårtensson. And a couple of years back, Magnus was traveling to the US for a conference, and he got into a little bit of trouble at the border. Magnus is from Sweden. And the Swedish rules that the Swedish government use when they make Swedish passports says that if you have this A with a little circle over the top, it's the O sound, that is AA if you have to render it in ASCII. So the little strip at the bottom of Magnus' passport says MAAR, Mårtensson. But the company who printed his airline ticket, they don't know about the Swedish government rules. They're just like, it's an A with a circle on it. We don't know how to print that circle on our mainframe. All right. Who cares? Take the circle off. So Magnus gets to the US with a passport that says MAA and a ticket that says MA. What do you think happens? Well, yeah, the US border control, they're famously cosmopolitan and open-minded people, and he had to answer some fairly difficult questions. And, you know, Magnus is an affluent, charming white guy traveling to a software development conference from Sweden. You know, he's probably the least threatening person there is. Imagine how this experience might have played out for all kinds of other people who have the same problems, all to do with how do you translate characters into ASCII. It gets worse. Here's a list of cities in Europe, and what we are going to do is we are going to take this set of cities and we are going to put it into alphabetical order using Microsoft SQL Server. We're going to create a table of cities, and we're going to insert some values, and we're going to do a select star, and there we go. Berlin, Aachen, Zurich, Aarhus, and Örebro. Now, if we select star from cities where name equals Örebro, hang on. It's definitely there a second ago, right? So let's have another look. What do we got? Let's say, okay, well, if Örebro equals Örebro, print yes, else print no. But surely those are the same, I say, as a British English person who is ignoring the two little dots. That is because I'm using the wrong collation. If I say use Latin general, case insensitive, accent insensitive, CIAI, now they're the same because the umlaut is getting ignored. Now, let's have a look at what happens if we try and put these cities in alphabetical order. We've got select star, order by name, and that's going to give us Aachen, Aarhus, Berlin, Örebro, and Zurich, yeah? Now, if we switch that from Latin general collation to this thing, the Finnish-Swedish collation, and we run it again, Aachen, Aarhus, Berlin, Zurich, Örebro. Örebro is now at the end. The O with the umlaut has been moved after Z in that alphabet, but now we're going to do the same thing using the Danish-Norwegian collation. Boom, look at that. Berlin is now the first city in the alphabet. Aachen, AA, no, that's at the end. And Aarhus, AA, that is also at the end. And you're looking at this and you're probably thinking, what? Well, history, my friends. The city of Aarhus is the second largest city in Denmark. This is to do with the rules of Danish and Norwegian orthography. And the city of Aarhus was officially spelled Aarhus, like this, not like that, from 1948 until 2011. Now, the reason for this is something called the Danish spelling reform. In 1948, Denmark decided that they wanted their spelling to look more kind of Nordic, Scandinavian, and less Germanic, for reasons you can probably figure out. So they added 3 new letters to the end of the Danish alphabet, and they changed the spelling of a whole bunch of Danish names. So Aarhus became Aarhus. New letter that's now at the end of the alphabet, so now Aarhus moves to the end, and it appears after Zurich. But then in 2011, the people of Aarhus voted to change the spelling back, I think because it would work better with internet search engines and that kind of stuff. So they changed it from the O with the circle on top back to OAA, but they didn't move it. They said the rules of Danish orthography say that if it's a place in Scandinavia, that's O, that goes at the end because it should have been spelt with one of these at certain periods in history. And so we have this bizarre collation now where if you run this list in alphabetical order, you kind of need to know what country the city is in to know where to put it to properly respect the rules of Danish and Norwegian orthography. If you have to solve this in software, the only way to do it is you need to go, right, we're going to have 2 columns. We're going to have a name and we're going to have sort name on our table here. And if the sort name isn't the same as the name, we're going to have to override the alphabetical order here in order to do that. And you get weird little quirks like this popping up all over the place. In the UK, we have weird rules about where you put McDonald in a telephone book because we alphabetize it as if it had an A in it, which isn't really there. And I've found other, weird cases from all over the place. But, you look at that. If you go onto a Norwegian copy of Windows and sort files alphabetically, aardvark will appear at the end. And you'll be like, why is that? And it's history. It's politics. You cannot separate technology and politics because so often human beings and politics and decisions, they just get incorporated into what we are trying to do here. You think about what the Unicode consortium was doing. Unicode was not trying to tell people how to write. Unicode is just trying to say, well, this is what human beings are doing. Let's come up with a way of encoding it. Let's see if we can figure out a way of just capturing what they're doing that allows them to communicate with each other better using the conventions that people are already used to. So when we get a character like this one, the C with a Sadia accent underneath it, in some alphabets, that is a letter of the alphabet. In some alphabets, like British English, it's not. The way we do it is we take a regular C character, ASCII code 43, and we draw this little thing underneath it, the Sadia. Now, this thing here, U0327, that is called a Unicode combining character. The thing about combining characters, you can add them, and it just says, draw this onto the character that preceded it. Add this to the last character you saw. And you can put more than one of these on. You can take like a Z and you can add a one of these and a one of those and a one of those and a one of those and just keep stacking them up until Tony the Pony gets a little bit unhappy because Zalgo is coming. And this is how Zalgo text works. It's ordinary text with a whole load of Unicode combining characters, all just kind of stacked one on top of the other. And sometimes it works and sometimes it crashes iPhones. And it's just, it's all part of the standard. There's nothing kind of, illegal going on here. The standard allows you to do this. It's just an edge case that a lot of devices can't cope with. But let's go back to Francois, the French archaeologist. In some alphabets, we'd write his name like this, with a Sir Cedilla character. In some other alphabets, we'd set it as a C, and then we'd put a combining character afterwards. And now we've got a problem. We've got two strings here that they look the same, they sound the same, and they mean the same thing, but they are not the same sequence of bytes. They are not binary equivalent. How do we know if we're doing like a text search in a text file, or we're doing some kind of spell check routine, or we're Googling and looking for stuff on the internet? How do we decide whether two pieces of text are the same or not? Now, this is where Unicode solved another big problem, is they created a thing called Unicode normalization. There's a little chunk of code here, and you can find this at the URL. I'll share that afterwards. And Unicode defines 4 forms of normalization. It says there's a C is composed and D is decomposed. So C says mash everything together into the smallest. If you've got a C with a cedilla, combine them. Compose them, make that a single character. Decomposed does the opposite. It says take whatever you got and break it out into the largest number of characters possible. And then the K here stands for canonical, because C was already being used for something. And canonical says, never mind do they look the same, do they mean the same thing? Let me demonstrate an example. So what I've done here is I've got the word buna, but don't worry about the pronunciation too much. There's 2 ways of making buna in Unicode. One is you just put B-U-N and then A with the breve on top. The other one is B-U-N, regular A, like an English style A, and then you add a combining breve character onto the end. Now these will look the same and they will print the same when I print them onto a console. We want to know, are they identical? Well, if we compare those two, let's run that little program and see what we get out. String 1 equals string 2, false. They are not the same string according to .NET's object comparison rules. However, in the composed form, they're equal. The decomposed form, they're equal, and both canonical forms, they are equal. So however we want to, analyze it, these strings mean the same thing. They look the same, they mean the same thing. Let's have a look at another example. So if we have a salute here, and we've gotten an salute, but this is spelled using bubble characters. Because Unicode also has a whole bunch of alphabets that look different. They're not different fonts. They're the same font, but with different character glyphs encoded in the specification. So S1 equals S2, are these things the same? Now, if we run this through our little program here, what we get at the other end is they're not the same string, and they are not the same in the composed or decomposed form. But if we invoke the canonical form, then they are equivalent, because they are the same letters from the same alphabet. They're just not the same versions of the same letters. You ready to believe me yet that there's no such thing as plain text? Because I'm going to tell you a story. A couple of years ago, I'm sat at work one day, and one of our sysadmins comes over to me and says, dude, I think we've been hacked. Now, we get this all the time. I've been hacked. No, you haven't. That's just you've accidentally opened the console. I've been hacked. No, you haven't. You just don't know how to read your own email. I've been hacked. No, you're holding your phone upside down. However, on this occasion, the person saying we've been hacked was a very, very good security engineer who was brilliant at his job. So when he says we've been hacked, I'm like, all right, why do you think we've been hacked? there's Chinese in the Windows event logs. I'm like, okay, this is good. So we open up the Windows event log, and sure enough, there is Chinese in the Windows event logs. Now, we are a British company based in London, no Chinese customers, no Chinese employees, no Chinese programmers. There's no Chinese content in any of our systems. So whatever this is, we've got no idea where it's coming from. So it's like, right, one of the team, you go start looking through the firewall logs, see if there's been any attacks. You go and start looking through the database itself, see if there's Chinese in any of the tables. Maybe this is like a SQL injection attack. And you know, the thing about managing a team is once you've given everyone else something to do, you have nothing to do because you need to be available in case more management is required. So I went to my desk and I got on Twitter and I put on this: the incoming tabular data stream TDS RPC protocol stream is incorrect. It's going to be one of those days. And I got a reply within a couple of minutes. Oops, that looks like Unicode mapping, UTF-8 being treated as UTF-16. And then someone else said, the low bits are all null. So this is probably UTF-16LE being mistaken for UTF-16BE. And I'm like, I have no idea what any of these things mean, but now is probably a good time to find out. And so I do the most intensive crash course in UTF-16LE versus BE that I think anyone has ever done. And within about half an hour, we start kind of figuring out what's going on here. Now, we can't fit all the Unicode characters in the 8 bits of ASCII. There are too many letters. So we end up overflowing. Now, Windows and Java and JavaScript and a couple of other systems, what they do internally is they just say, all right, every single character, we're going to use 16 bits, 2 bytes. And then you have a problem because you have 2 bytes. Which one's the big byte and which one's the little byte? If it's first, it's big endian. If it's second, it's little endian. And there are disagreements as to which way is the correct way of doing this. So if you take a character like delete or a string like delete, if you look at what is in memory on Microsoft Windows, each of those characters has 2 adjacent bytes, 16 bits, 2 times 8. The first one is 0044 because it's ASCII 44, 65, 60. Yeah, you know, nothing terribly controversial here. This is all kind of familiar stuff. But if you flip those pairs around, if you go big endian versus little endian, what you get out the other side is Chinese. The first character here we ran through Google Translate in case it was like a ransom note. I think it means to place a pearl in the mouth of a dead relative. And the second one is to prepare a chicken for ritual slaughter. So that didn't really help us very much with anything. But this made sense. It's like, this is a good lead. We can follow up on this. So next question is, why has our dynamic CRM server suddenly flipped from big endian to little endian? What's happened there? What happened was one of the pieces of virtual network equipment in our data center was having a really bad day, and occasionally, about every 5 minutes, it would drop 1 byte from the data stream between the CRM server and the database. And when it dropped that byte, everything else would get shifted sideways by 8 bits. And then the thing on the other end would try and reconstitute the character stream without realizing something was missing, and we would get Chinese out the other end. So that was the day that I discovered the joys of big endian versus little endian and UTF-16 encodings, and learned a couple of interesting bits of Chinese orthography that I never thought I'd need in my professional life. We eventually rebooted the network switch and we solved the problem. But this is just one of the encoding systems that we've used to take these millions of characters in the Unicode specification and try and cram them into something that computers can understand. The one that's used on most, certainly used all over the web, it's used on most devices, most editors these days, is an absolutely brilliant system. It is called UTF-8. Now, UTF-8 starts with a rule that says any byte starting with a 0, that's 7-bit ASCII. That means the same thing that it used to mean back in 1968. That has not changed. If it starts with a 1, it is part of a multi-byte encoding sequence. So look for something with 1, 1. And see how many 1s are at the beginning of that. In this example here, 110 means this is the start of a 2-byte encoding sequence, and a 10 anywhere means this is a continuation character. You need to rewind, find the beginning, and count from there. If you need to encode 3 bytes in a Unicode character, 1110, and then continuation characters, 11110. In theory, UTF-8 will go up to 8 bytes, which is 2 to the 256, which is basically more atoms than there are in the universe. In practice, they restrict it to 4 bytes because that means you can round trip it to a system called UTF-32, which is a fixed byte, 4-byte encoding system. You still think there's such a thing as plain text? Yeah. But UTF-8 is brilliant. All the ASCII is still ASCII. You don't waste a lot of overhead encoding characters that aren't necessary. And even if, think about something like publishing a web page in a Korean or Arabic or Hebrew, all of your markup is still ASCII. All of your HTML attributes and your CSS rules and your JavaScript are still ASCII. So all the stuff that's ASCII still compresses down as small as it ever did. And it's only when you need the headroom to start incorporating extra alphabets and all that kind of stuff that the additional encoding and traffic overhead of UTF-8 kicks into play. Now, this is good. We need headroom because humans do not stop inventing languages. In fact, there is a new language. It's a language that most people on this call are probably reasonably fluent in, even if they don't recognize it. It is not a spoken language, and it is less than 20 years old. It was created, actually, it's just over 20 years old, created in 1999 by an artist in Japan called Shigekata Kurita. It's working on a system called iMode. Japanese phone company Docomo they were building some of the first smartphones. They wanted a nice way of showing information visually. They hired this artist who created Emoji, the original set of 176 emoji. Now, this set of emoji is currently on display at the Museum of Modern Art in New York. Initially, it was just a big deal in Japan. All the Japanese handsets rolled it out. What really kind of blew the lid off emoji was when Apple launched the iPhone in Japan in 2008. Now, to sell a phone in Japan, it had to support emoji, otherwise no one would buy it. Apple added emoji to iOS. Lots of people around the world suddenly worked out that if they set their region to Japan, they could type all these cool little characters and smiley faces. The Android people went, they've got that, we need that. Android and Apple put their heads together and they went, this is actually going to be important. Maybe this is one of those things where we should collaborate, like they did on the COVID track and trace protocol earlier this year. It doesn't happen very often, but when it does, it's a big deal. And Apple and Android jointly sponsored Emoji as an extension to the Unicode standard. Emoji became part of Unicode in 2010, and it spread around the world, and people started asking questions. And some of them were innocuous questions, like, why is there emoji for sushi but no emoji for tacos? Like, well, it started out in Japan, no big deal. Why are the emoji for the doctors and the engineers and the police officers all white guys? I mean, technically yellow Simpsons kind of people, but almost all the emojis for professions and things were depicting cartoon Caucasian male figures. In 2015, Emoji took a massive step forward with Unicode because they introduced a way of changing the skin tone on characters. So, for example, you could take thumbs up and you could add this, the 1F3FE, medium dark skin tone, and suddenly you could do a thumbs up that looked the way your actual hands looked. And they came up with a whole bunch of extensions on this format. If you look at the latest set of characters that have been added to Emoji, there are loads of them. There are different family configurations, different kinds of couples, different animals, different Santa Clauses, and all this kind of stuff. And they haven't given code points to all of these things. What they've done is they've used something called a zwidge, a zero width joiner. So if you take the female astronaut glyph that we have in Emoji now, what's actually going under the hood is that is woman, zero width joiner, rocket. If your handset or your device supports it, you get a female astronaut. If it doesn't, you get a woman next to a rocket, and you can work out the rest yourself. And if you want to introduce you to one of my little desktop mascots here, oh, the space shuttle's fallen off. This is Mae Jemison, who was the first African-American woman in space. Now, I am not going to go out and tell Mae Jemison that she cannot have an emoji. I don't recommend anyone try that. Instead, what we are going to do is we are going to say woman plus dark skin tone plus a zero width joiner plus a rocket. And now Mae Jemison has her own representation in Emoji. And pretty much any combination you can think of ethnicities and professions and family configurations and stuff. Now, one that's really interesting is the way Emoji treats flags, because it does it in 3 different ways. If you take, for example, the flag of Belarus, there's a set of tags in Emoji that represent letters of the alphabet used for tagging purposes. And if you take a B plus a Y in that, that will give you the Belarusian flag. The flag of England is not a country, according to ISO. England is part of the Great Britain of United Kingdom and Northern Ireland, blah, 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 blah. But England has a flag, and the way that flag is drawn is it is the black flag combined with G and B. And this is used for England, Scotland, Wales, and I think the flag of Texas is in the latest version of Emoji using that same approach as well. GBENG. And finally, there are certain other flags which are not geographic flags, like the pride flag. The pride flag in Emoji is the white flag, a zero with joiner, and a rainbow. That's how that one's been portrayed. Now, does anyone know what flag this is? This is the flag of a country called the Republic of China. We don't know it as that. We know it as Taiwan. It is not the same as the People's Republic of China, which is a much, much bigger country. And the political history between these two countries is complicated. If you go onto an iPhone and you type in Taiwan and you press the flag emoji, you can get the flag of Taiwan. If you go into your settings and you change your region to China mainland, the Taiwan emoji disappears. The flag is not there anymore. It's not on the keyboard and it won't render it, because displaying the Taiwanese flag is a good way to get locked up if you're in mainland China, and China has a lot of people buying a lot of phones, and Apple doesn't want to upset them because that would be bad for revenue. So different handset manufacturers and devices solve this in different kinds of ways. If you're on Microsoft Windows, go onto my Twitter profile, have a look. You'll see next to my name is the flag of the European Union. But if you go in to edit my profile, which obviously you can't do, but I can, that flag disappears. It just becomes EU. In this view, that is Twitter showing you a little PNG by doing some transcoding on it. The actual character set on Windows does not include any regional flags, probably for the same reason as Apple does not include Taiwan. They don't want to get involved in a political fight about whether a certain government is going to buy their operating system because it includes the flag of a country that they don't recognize. Politics, technology, you still think there's such a thing as plain text? Because this is all text encoding playing out on a grand scale. Interestingly, the flags that Windows does support is it's got the pride flag, it's got the transgender pride flag, and it has the pirate flag. So Windows says there's no countries allowed, but gay pirates is okay. Which if you're going to adopt a mission statement, that's probably a pretty good one to work with. Now, the home stretch, I just want to introduce you to one more wonderful little edge case to do with how we render plain text. If you have a look at the logo for my company, look very closely at the T and the I there. They're joined together. That's not a graphic. Under this is ordinary ASCII, URSATILE, but I'm using a typeface here called Lato that supports something called ligatures. Now, ligatures are cool because a ligature is a way inside a font of saying, if you see this character and this character, glue them together and replace them with this symbol here. And there is a programming font. Take a look at this chunk of F# code here. Now you're looking at that thinking, wow, what are these triangles and these arrows? Is that normal? Now what's under here is this. This is normal F# source code. These are the same file rendered in two different typefaces, but one of them is using this, the Fira code typeface. Now, Fira code is a brilliant programming typeface full of ligatures that you can use to do all kinds of cool things. And it just makes your code look awesome and readable. You get things like a triple 3-bar equals for the triple object identity equals in JavaScript and stuff. So if you want to take away something cool you can install and use after this talk, go and check out the Fira code typeface if you haven't already. And I'm going to leave you with a little piece of information. I'm going to invent what we call a shibboleth for all of you, because I was in Belarus a few years ago, and I started learning to read Cyrillic several years because I think the whole, kind of Slavic languages and Cyrillic alphabet I think is really, really interesting. And something I noticed is that in Belarus, I couldn't read the road signs and I couldn't read the restaurant menus, but I could read all the license plates on all the cars. And I thought, this is weird. Why, does Belarus use the English alphabet just for license plates or something? And I started doing a bit of research. I found out some really interesting things. There's a thing called the Vienna Convention on Road Traffic, 1968, the same year as ASCII. 36 countries, including what was then the Soviet Union, they signed an agreement that said if you were going to drive your car across an international border, you could only use the Latin, the English alphabet on your license plates. And the Soviets went, yeah, no problem. They signed the accord and they kept driving around with license plates that look like this. And somebody said, well, what if someone wants to drive their car out of the Soviet Union? And they went, you cannot drive car out of Soviet Union. And you're like, but what if they really want to? And it's like, well, if they can make it to the border, we'll give them some temporary license plates to show they took a vehicle out of the country and stuff. And then when the Soviet Union, collapsed in the 1990s, lots of different member states of the former Soviet Union adopted their own conventions that embraced the Vienna Convention on Road Traffic. And what they did is they took the Cyrillic alphabet and the Latin alphabet and they identified the set of characters in the middle that is the intersection of those two alphabets. And it so happens that if you take those glyphs and you write them in English and you rearrange them, they spell the phrase pike matchbox. So I want you to remember that, because next time somebody says to you, hey, I'm going to send you a plain text file, you look at them real close and you say, do you know pike matchbox? And if they say, then you know they've seen this talk, and you know they know about big endian and little endian and character encoding and ASCII character sets and all this kind of stuff, and that the plain text file they send you is probably going to do what you think it's going to do. And if they say, what's pike matchbox? You're on your own, because there is no such thing as plain text. Mulțumesc. Thank you very much, Codecamp. That was a lot of fun.
Thank you, Dylan.
Talking, there they are. Hey, how you doing?
Thank you, Dylan. You are a rock star. I'm impressed. You're an exquisite speaker. For a couple of moments, I was thinking, God, I'm I don't know, a TV, right? Watching like a, I don't know, some history combined with science. You know, type of
stuff is always more interesting if you can kind of connect the dots all the way back to something in somebody's own experience. One of the things I love doing with technology is like, this is not just you know, something like the Danish-Norwegian collation there. It's like they didn't just make this up. Like, you know, you have to understand why Windows behaves the way it does. You need to know who lost World War II and what the political fallout and implications of that. And then people are like, all right, yeah, now it makes sense. I thought it was dumb, but now I understand the problem that they were trying to solve, and this happened, and then that happened, and then that happened. Yeah, I can see why you'd end up with aardvark at the end of the alphabet on a Norwegian copy of Windows. And then people remember it, and it kind of, because of the sort of storytelling and rooting it in historical fact, it becomes easier to relate it to real life.
Yep. So stories are magic. So until now, I thought world, you know, runs on code. It looks like it's world runs on clear text in many ways. So
most of it, just watch you don't get the bits flipped, or it'll start running on languages you didn't expect to be reading today, especially not in your event logs.
Yeah, so everything you said, I think it brought so many, let's say, painful flashbacks when you're handling these things or various names in the database. And also, we have a question, because I was going to say at some point, if I was looking into Teams, and there are no questions. I mean, now there's a feedback like, yeah, it's an amazing presentation, but there were no questions. So I was looking at the attendance. Am I the only one that is enjoying this? But the attendance kept rising. So it's all good, but everything was very clearly presented. Yeah, I can say, also coming back to our discussion when we started this whole thing, and you said, yeah, your way of learning is when you have a problem and then you solve it and maybe you study more around it. That's what you do. And then I saw it with the hacking incident, because probably that's when you started looking into all of this.
Yeah. Well, like I said, you know, my first experience of text encoding was trying to type a pound sign, a British pound currency sign, on a computer when I moved to the UK when I was 10, so I'd have been 10 or 11 years old, and being like, well, where is it? And then I had a computer where I could type it, but I couldn't print it because the printer was using a different code page to the WordPerfect on the desktop. You know, there used to be these computer magazines in the UK, and literally every month someone would write a letter into PC Pro magazine saying, I can't print a pound sign on my new printer that I bought. Why you're not? And they'd be like, tell them the code page story again, Phil. And it'd be like, whoa, code pages. And it's just, you know, it's one of those things that everything works up to a point. And for so many people, their kind of first experience of the computer doesn't work was when they suddenly needed to encode some text that was outside their, you know, the formatted, the supported character set of the device they were using. So yeah, my experience, like I said, goes back probably 30 years. And then the big endian, little endian, that really happened. That whole thing was absolutely true, right down to the Twitter thing and people going, yeah, big end versus little end is the wrong way around. I love Twitter for that reason alone. You say something on there and somebody will pop up and go, I think you have this problem. So
yeah. So to me, your presentation stands once again for the fact that, well, there is a lot of room for learning. I mean, because I must confess, without being part of this presentation, I wouldn't have thought in so much detail under the hoods of what's behind the code and so on. I mean, yeah, I've been doing that during time, but not to such level of detail. So there is space for improvement and for learning.
Yeah.
More and more.
It's the fun thing about writing a talk like that, you know, it's probably 5 or 6 hours worth of material, and you have to pick the most interesting hour. All these little tangents around, you know, the little bit at the end where I talk about ligatures, like I'm spinning out another, because I reckon I can do a 1-hour talk about how a computer puts one character on the screen. I reckon there's an hour talk in just how do you render hello world? How does hello world actually make it onto the display where you can read it? And that was going to be the last 5 minutes of the talk, and then it became 15 minutes, and then it was a 1 hour, and then it was a 2-hour talk, and I was like, no, this whole chunk has to go out and be put somewhere else. But I wanted to keep the fire code typeface in and explain a little bit about how that worked. But you know, once you start kind of untangling the threads, it's like debugging reality. It's fascinating.
So for us as engineers, how much should we dig under the hoods, under the cover?
So there's a great essay. It's called The Law of Leaky Abstractions, which I think is now called Spolsky's Law. The original essay was by Joel Spolsky, who did Fog Creek and Stack Overflow, all that kind of stuff. And his idea, which I think I agree with, although I haven't quite decided yet, is you should understand one level deeper than where you're working. So if you're, say, you're building a front end in Angular, you should understand a little bit about the REST APIs that it's talking to. You don't need to be an expert, but you need to know when you send a GET request and you get back some JSON, you want to understand a little bit. And if you're the API developer, you want to understand a little bit about entity framework. And if you're building the entity framework models, you want to understand a little bit about SQL Server or the database backend. And if you're working directly in SQL Server, you want to understand things like clustered indexes and partition strategies. And if you're working on, allocating space, hard drive space in a cloud center or something for databases, then you need to understand about, spindles and failover models and all these kinds of things. And, for most of us, we don't think about electricity as part of our job. We're like, you plug it in and it just works, and it's probably a UPS. But then if you look at the stack of people, this talk now, we're probably running through a whole bunch of data centers on Azure, and somewhere there is somebody who knows more about electricity than any of us can imagine. And we get to ignore it because that person's really good at their job, and the next person up knows a bit about electricity, and the person above that knows a little bit about building server racks, and the person above that knows a little bit about wiring servers, and the person above that knows about operating systems, and we're sat way up on the top of it, and we know about webcams and conferences, and we get to do our thing. If the webcam stops working, I know enough about kind of Windows device drivers that I can plug in a different one and poke around with it. And if that doesn't work, I'm like, I've run out. That's it. That's my one level deeper. So
yeah, that's a brilliant way of looking at learning. Yeah. Thank you.
And you definitely have to join us for next year, because we have a piece of feedback saying that no questions except that Dylan's doing a great presentation on any subject. I'm in.
Yes, I'm counting 1, 2, 3, 4, like 5, in a row.
I tell you what, I'd love to. I was in Cluj-Napoca at the beginning of the year, and I was supposed to be in Iași in May, but that fell through because of the whole COVID thing. But one of my favorite things to do in Romania is go and see live metal with Romanian lyrics. Because the way the language sounds, it's like halfway between kind of Slavic and Romantic languages. So for like operatic metal, it's fantastic. I saw a band in Cluj last year who were just absolutely phenomenal.
And we can recommend you another one, Alternosfera.
Alternosfera. All right.
I'll send you the link.
Yeah, cool. All right. And yes, I would love to come. I'll see you there. All right.
Thanks a lot again, Dylan.
Thank you. Take it easy.